Life on our planet is possible because of the sun. Without it, we would find Earth to be a cold, dark place, a dead planet, among others. However, over billions of years, as life exploded on Earth and evolved into the incredible diversity of species we know today, our sun has been living a life of its own. The life cycle of a star is a forceful, violent process, the effects of which will eventually have a huge impact on our world. The energy emitted from a star is the product of fusion. In the fusion process, hydrogen fuse into helium. First, two hydrogen nuclei collide, releasing one electron along with energy. The nuclei eventually form groups of three. When two such groups collide, four hydrogen nuclei will form one helium nucleus. This is possible since four hydrogen atoms, like the single helium atom, possesses four protons. Two redundant hydrogen nuclei are able to restart the process. As an increasing amount of hydrogen turn into helium, the combined core mass will decrease, since four hydrogen atoms are slightly heavier than one helium. The extra mass turns into energy and is emitted as gamma rays. Because of the mass lost in the core, its outward pressure will weaken, while the outer layers of the star will press inward, making the core gradually more compressed. As this goes on, the outer layers will expand, increasing the star's radius, making it a red giant. Finally, the core won't be able to withstand the outer pressure, causing it to collapse. With the sun radius multiplied several times, one would assume this to have a great impact on the Earth. Let's see what happens. Earth is the only planet with life that we know of, one of a kind in our solar system, possibly even in the entire galaxy. What makes it so special? There is an area around every star inside which the amount of heat and radiation are suitable for evolution of life. This area is called the habitable zone. The Earth orbit is well inside this zone, and this provided excellent conditions for life to develop over billions of years. In addition, Earth has a protective atmosphere with a natural greenhouse effect, making it neither an icy desert like Mars, nor a burning pit of hell like Venus. In order to predict the possible evolution of the Sun from now on, I have studied other stars with roughly the same mass and chemical structure. The life cycle of a star is decided mostly by its mass, and so I hope to get a reliable view of the future of our Sun by looking at the fates of other very similar stars. From my research, I was able to make this graph. The vertical axis shows the radius in solar units. The horizontal axis shows time in billions of years. Although you might not see it very clearly, the radius increases steadily after about 7 billion years from the star birth. Judging from this graph, solar mass stars end their main sequence trip at about 10.5 billion years of age, with a radius of about 1.4 times that of the current Sun. So what does this mean? This formula allows us to calculate the average temperature of a planet based on some key facts concerning its star. We assume life is possible between 273 and 343 degrees Kelvin, the temperature range allowing abundant water on the planet's surface. This lets us put T as 343, which enables us to solve the formula as an equation. Doing so, I find the radius to be 1.34. Now, I can use the graph to determine at what age this number is reached.
As time began to burn, like a startling sign that fate had finally found me, and your voice was all